I want to welcome everybody to this for colloquium Roberto Tempo. The colloquia, you know, are organized by the Italian chapter of the Quantum Systems Society in collaboration with cnr-ieiit and this year with Politecnico di Milano, that I really thank for the hosting here, in memory of our colleague Roberto, who was a leader in the field. I think Frank will provide some of his memories of Roberto, and very thankful for that. So this is the for colloquium. The colloquium invites outstanding speakers from the quantum system community around the world. And for this for colloquium, I'm very proud and honored to invite on the stage Professor Frank Allgöwer. Frank is chair of the Institute of System Theory and Automatic Control. I'm not gonna give we usually don't do a bio of the speaker because you're well known and everybody knows you, and that's the tradition. So thank you very much, Frank. Just a few reminders before leaving the podium. First, for the people who are online, the talk is being recorded. So if you don't want to appear, please switch off your camera. And for all people here, there will be a light aperitivo offered by Politecnico di Milano after the colloquium. The aperitivo will be held just outside. But I mean, we will go together, but don't go away. And that's it. Please, Frank, you are welcome. The title of Frank's talk is MPC is going data, a data-driven MPC scheme with theoretical guarantees. So thank you very much, Frank. Thank you.
So thank you very much, Fabrizio, for the kind words, and thanks very much to everybody involved in the organization. I understand these were many people, Maria, Fabrizio, and so on. It's for me a big honor to be here, and also a very big honor, not only because I like to give presentations to distinguished audience, of course, but also because it's the Roberto Tempo colloquium, and I'm also very happy to see Roberto's wife and sister here in the audience. And let me start by also sharing a memory with with Roberto. And here you see a picture that probably no one of you has ever seen, because I took it, and we were sitting in the airplane right behind each other. And this was Roberto looking out the window. And he looks critical, I would say. And so I want to show you what he's looking at. This is what he was looking at. Seriously, these are pictures from that day, the window before Roberto's, pointing outwards. And for those who are experts, this one, I believe, is Mount Everest. So this was in the Himalayas, flying in a little aircraft. Here you can see the aircraft over the mountains. And this was, we were both, Maria was also there at this colloquium, was IEEE International Conference and Control applications. Automation, I believe it was called automation. It would be surprising if I'm at a conference for application. So I think it was automation. It was in Kathmandu, and Roberto and I, we sneaked away during the conference to go on that trip with Jetty Airlines, this animal that lives up there in the mountains and looking at the mountains. And here you can see that Roberto was not always looking this critical, but he was really smiling. And in fact, he had the time of his life. And so me also looking outside the window and enjoying this trip. So what was he really thinking? I have no idea, but I have a guess. Huh? So he was looking at those mountains and saying, hey, yeah, sure, I'm coming back to to have those. So we are definitely missing Roberto very much. And as I said, for me, it's a great honor to be a speaker in that colloquium series. In fact, I will be talking about model predictive control. Now comes a purely scientific talk, or let's hope you also see it as something scientific. And I think something that Roberto would have liked. It did not exist by the time we were collaborating also on MPC together also with Fabrizio. We're doing or still doing stochastic MPC. Here is a new idea, and I'm pretty sure he would have liked it. And I'm going to explain that to you over the next minutes, 45 minutes or so that I will talk. So what are we facing today as control engineers? We are facing awfully complex problems. It's not that we have one control variable that we have to control. No, it's make a car self-driving, make a robot walk. So make a drone fly, do something, take pictures, whatever. In health. So there are very complicated processes that we have to deal with, and all our methods have to be able, if they are to be used in practice, should be able to deal with such systems. So we have tremendous complexity, much more than we usually have. We have this autonomy, we have networked systems, distributed system, intelligent parts, some learning inside, and all our methods, they have to be able to deal with this kind of environment. Therefore, we have for control really a wish list. So if we want to judge a method, then this method should be able to deal with complex systems, should be able to deal with nonlinear systems, highly dynamic systems, systems that we partly don't know, partly know, but maybe some things we cannot really model, where we have measurements that are potentially very bad, and we want to achieve a lot. So in the end, I want to come back to that slide here, and we will go through that, and then we decide jointly whether the method I'm going to show you addresses all those problems. And I believe it does, because it's a combination of data, models, and prediction in the system, and having still control theoretic guarantees. So, and the method I'm going to talk about is model predictive control. Not really a surprise if you see me. And just to starting out, to be sure, I know there are even experts in the field, people who are in the field much longer than I am, Ricardo, for example. So no need to explain MPC to most of you, but maybe there are some people who do not know it yet, and therefore I will briefly give an introduction. So what does MPC do? MPC solves an optimal control problem. Nothing else than that. It's optimal control 100%. So given any method to predict the future of the system, so normally we say, given a model of our system, hey, I'm generalizing it here somehow because we want to use data, and we want to find a stabilizing strategy that minimizes an objective function over an infinite horizon. That's the thing we are interested in. And we have some constraints that we want to satisfy. So how can you solve that problem? There are various ways how you can solve such an optimal control problem. One is optimal control theory. 70 plus years old, lots of beautiful results that are there. So finding or characterizing how a feedback, what properties a feedback has to satisfy in order for the closed loop to have optimal behavior is known. Hamilton, Jacobi, Bellman, Pontryagin, you know, all the names that we have in that field and that wonderful theory. So we get very nice results there, but they have all a drawback, namely you cannot compute the controller. It's just, except for toy problems, it's not possible to compute it. So wonderful theory, but not really very useful. Now, what's the alternative? The alternative is that we think more locally, that we are not trying to find a feedback, a u as a function of x, but assuming we know where we are, assuming we have our x, let's try to find a function of time, an open loop control, a u of t, assuming we know where we are, a u of t into the future, that solves our problem. So that's a different sort of problem that we are doing. And this has the advantage, yes, it can be done. You can solve that in a good way, but you do not have a feedback. Now, what is MPC? MPC is really trying to bring those two things together. Use the computational complexity on the right-hand side and implement it in such a way that you get a feedback solution. So you're not solving the problem only once, but you are solving it repeatedly. You're solving it all the time. So you find a trajectory, a u of t, over the infinite horizon that minimizes your objective functional, satisfies your constraint, and so on. And then you discard everything of that solution trajectory except for the very first step. So why do we have to control the whole thing? Bellman's principle of optimality, only n pieces of optimal trajectories are optimal. We have to compute the whole thing in order to be able to apply the first thing. And then we are doing that over and over again. And of course, going over the infinite horizon is not really the thing that we can do. So computing the trajectory over an infinite horizon is not possible. Therefore, we go to a finite horizon. So finite horizon is not a feature, but finite horizon is the problem. We have to go over a finite horizon. We would love to go over an infinite horizon, and actually all the control theoretic problems would go away if we could do that, but we cannot. We can only go over a finite horizon for practical reasons. So here, the cartoon that you all know. So there is we are currently here in time. This is the time axis. This is the predicted future. This is the actual past that happened. We know where we are. And then over a horizon that I call n here, over a horizon, we try to find an optimal input trajectory that minimizes our cost function. And then we are only implementing the very first piece, throwing everything else away and make the next step. And then we are solving the problem again. And the problem will be different that we are solving at that time because our horizon shifts. So we are looking further in the future. So it's not the same problem, but there is a very close connection to it. So like in chess, where you plan ahead into the future, 100 steps or whatever you do in your mind to think what you do then in the future, and then you apply your first step, and then your opponent, we would call it a disturbance, makes the move, and then you are reconsidering, hey, maybe I'm going with the same approach, but maybe you're playing against a stupid person like me, and then you change your strategy and you think again over 100 steps and make a different strategy. So it's exactly the same what MPC does. So what we have to do is solving online an open loop optimal control problem. So the same that we had before, minimizing an objective functional, now over a finite time. And we want to find a U trajectory over our infinite horizon. And we want to do that based on our future that we compute with a model, on constraints, on the states and on the inputs. And this is the problem we solve. Now in MPC, the big problem in MPC theory is that this does not lead to a stabilizing solution. So it may go unstable, and in fact, it's very easy to construct examples where it really goes unstable. So you have to do something, and one of the approaches, what you can do is you add those blue terms, a terminal weight and a terminal penalty term and a terminal constraint to your system. And MPC theory, classically, the last, 25 years, is how to compute this VF and this XF down here, such that the closed loop has nice properties. So this is MPC. Now, why does that work? And why do I explain that to you? Because later on, we are using data. And of course, the obvious thing with data is you do some learning. And most of those things, in my opinion, are just stupid that people do. And the reason is that. So why does MPC without data work? The reason is that we are solving the problem locally. So the optimal control problem that we want to have, the U as a function of X, you have to solve globally. Here, we only look locally because we know where we are. If we are in that corner of the room, we can find a solution, but we have no clue what would be necessary in the other corner of the room. So we only need a local solution, and it's not the finite horizon, as many people who are not in MPC believe, that makes our life good. The finite horizon is our enemy, or the one that got me interesting control problems over my whole career. But it's that we can solve it locally, this problem. That is the reason. Now, MPC is very much applied in industrial practice. The main reason is really not that it's optimal, but mainly that you can deal with constraints. That is the reason. And here is a survey from IFAC's industry committee, one of the IFAC committees, and they have asked quite a few companies, I believe it was 2,000 companies, they asked in 2018, what are the control methods that you are using today? And what do you think in 5 years, which is 2023, which is now, what do you think is the methods that you will be using and you think are important? And as you can see, in 2018, already model predictive control was pretty high on that list. But the prediction that they had in 2018 is that then, hey, in 2023, model predictive control will be all over the place. I don't think that this will be the case. If you ask people now, that will be exactly the same outcome of the survey. But nevertheless, it shows people in industry are interested in model predictive control, and it's something that works. The good thing there is we can deal with control theory. We know how to formulate the problem. We know how to compute the solution. Everything is very well understood. But there is a but. We need a model. And if you don't have a model, then you have a problem. And usually if you have a control application, then getting the model is the most difficult, the most time-consuming thing. So the obvious thing to think about, hey, we are living in the world of data. So all around there is data. People are not interested in models anymore, it seems. So let's just use data. This is the cover of The Economist a couple of years back, I think 2017, where they said data is the new oil in the world. Let's just use data. And the learning. So of course, the obvious reflex that you have, everybody is doing machine learning, artificial intelligence. Let's just learn our stuff. We don't have a model. Let's just learn the model and apply something. There are tons of things that are being done. Most of them, in my opinion, stupid. Some things really good. And everything that people in the audience are doing is, of course, on the perfect side. So please don't feel insulted. So you can learn, of course, the control law. Reinforcement learning is essentially solving that problem with the different means. You can also learn, of course, the cost function, the model. You can learn the constraints. There are tons of things. And I was writing down here hundreds of articles. It's not true. It's hundreds of articles per day, I have the feeling, that are published in that field. You use your learning method 1 with MPC, you combine it and you have a small example and you publish that. So this is not what I am going to talk about. No learning in a direct sense in my talk at all, but using data, because I think the data is really the new thing that we have plentiful and that we can deal with. So no learning anything here, or only in the very end, I make a comment why this method can be considered as learning. What we want to do is use data in a different way, and the basis we do is Willems' fundamental lemma, which probably also everybody in the audience knows, but nevertheless I'm going to repeat it. And then I will go through that chain of parts here. First, talk about model predictive control, using this data for linear systems, then adding noise, robustifying things, and then going to the nonlinear world. So what is Willems' fundamental lemma? Willems' fundamental lemma is actually an approach that Willems and co-workers looked at in the context of identification. So you have a linear system that you excite with some input trajectory, you get one output trajectory, and you assume you have an unknown system, a linear system that you do not know. Now, is that a good experiment that we are having? Do we get enough information out of that experiment, UD, YD? And of course, but if you just insert into a linear system 0, you get 0 out, you have no information about the system at all. Also, if you use constants, no information that you're getting. So what are good inputs? What are persistently exciting inputs? And that was the question they answered in their paper. And the answer is surprisingly simple, essentially a consequence of superposition principle for linear systems. So we have an input trajectory, and we just use that input trajectory that we have over a certain horizon, over this horizon n, and we take that input trajectory and use the first elements of that input trajectory up to this capital L element. This L later on will be in quotes. I'm not going into any details here, and it's not absolutely correct, but it's related to the dimension of the system that we want to find out. So this L is essentially, what do we think, which order does that system have? And if it is hundredths order, we need more data. If it is only second order, then we need less data. So this L is essentially what we have. We have a longer trajectory than this L, and then we shift our trajectory by 1. So not U0, U1, U2, but U1, U2, U3, U2, U3, U4, and so on. You shift until you run out of data, and you put that into a big matrix. Now, this matrix has a Henkel structure, so the cross diagonals, or I'm not even sure how that is called, are the same. So that's U1, U2, U2, U2. So this matrix you have, and now the persistency of excitation result that they have is UD, this input trajectory that we are having is a good input trajectory, gives us enough information to find all the dynamics up to order L if that matrix has full row rank. So it's a very beautiful result. You can check whether your matrix is good, assuming you have no noise, you have a linear system, and so on. Now, but the interesting thing here is that you can use that also to characterize the dynamics of the system. So not only to check whether you have good data, which you also need, but that you can characterize the system. So let's now assume we excite our system with such a data that is good, and we get one output trajectory. Now, can we capture the whole dynamics of that system using this input-output trajectory pair without doing an identification? So no computation needed, just we want to have a characterization for our system. And this is indeed possible, and that's also a consequence from Willems' fundamental lemma. Actually, it's also in the paper. So you are not only doing this Henkel matrix for your input trajectory, but you're doing the same for the output trajectory. So you get two Henkel matrices, and you stack them up together, and now the range of that matrix gives you all the trajectories that this system can have. So if you plug into, this is a constant matrix, just a constant matrix where you edit the trajectory, so no computation needed, you just fill the matrix, and now you multiply it with a constant alpha of appropriate size, just a constant vector, and you are getting a trajectory pair U bar, Y bar. And if you vary all the alphas, all of the results are trajectory. And in fact, it's a characterization if and only if. So for any U bar, Y bar trajectory, there exists such an alpha. The proof in one direction is one line. The proof in the other direction is much more involved. And there are still papers coming up trying to simplify the proof in the other direction, giving more insight. But nevertheless, it's understood. It's superposition principle. Actually, in some of the talks I gave in the past, people afterwards were saying, hey, this is a trivial result. Willems would be insulted to call it after his name. I wouldn't if I were Willems, but it's indeed, it's superposition principle that we are using. So we have a way how to characterize the dynamics of our system. It's a model in quotes of our system, but it's a data-based model because you just plug in the data of one trajectory, one single trajectory that you take offline for which you check whether it's persistently exciting. So just a rank condition that you have to satisfy. And then you have a constant matrix here, and this gives you a way how to characterize any dynamics of the system. So, of course, once that was realized, which took 10 years, more than 10 years after Willems' paper, that people realized that you can use that as a model. So you can analyze the systems. You can analyze any property or almost any property of a linear system this way, just using that description. Here are a number of papers, heavily citing myself. But there are many, many more people doing that. But you can also do controller designs. Sure, you have a characterization how U and Y relate to each other with over this simple alpha. So just formulate it. You can do LQR, you can do LQG, you can do anything. H infinity, you can really everything that you can do with the model, you can also formulate here. And now the idea that we are talking about it here is use that for MPC. So classically, this is the slide from before. We minimize our objective functional subject to our state space description of our system. And now we are doing something else, namely we are still having our minimization problem. So we have the quadratic, in that case here, the quadratic deviation from our set points, from our trajectories over a finite horizon here. And now we are having the model in a different way, namely we formulate the model in this Willems fundamental lemma form. We are just saying, hey, the U bars and the Y bars in our model, they are the outcome of this thing here if we plug in an alpha, and this thing here depends only on one trajectory that we took offline at the very beginning. So this is a constant matrix. So we use a different model, and really the only assumption that we need, hey, it's a persistently exciting model. So we can check that, whether it is the case, and we have to minimize also over this alpha. So that's a very simple control problem. And this is really the good news is for everybody, and there are quite a few people in the audience who are MPC experts, and I'm sure they agree. The output feedback MPC problem is not a simple one, but here we have an output feedback formulation. So it is by itself an output feedback MPC problem. So if we can prove something, it will always be for the output feedback problem. So now we have normally an initialization of our problem. We measure the state at a given time. At one point, you have only outputs of your system. If you measure the output, not all information is contained. So what you have to do is you have to take the past measurements, and you have to take at least any measurements as you believe your system has order. So we don't know what order it has. So we take this L. So this, I call it small n here, but it's the L from before, so that we believe this upper bound on our dimension that we have. So the initialization is a trajectory of past measurements with which we initialize our model. And therefore, we have an output feedback method, we have the constraints, and we do everything in exactly the same way as we do in classical MPC. So we solve that repeatedly, compute the whole U, the whole alpha, but only use the first step, implement that, measure again, add one measurement to our measurement vector. So it's a different problem that we are solving than from before, and then solve the problem again. So this, unfortunately, I cannot claim that this is my idea. This idea was the first publication that I know is 2015 by a group from Shanghai Jiaotong University. But their paper is not very much cited because there are so many mistakes in that paper. But nevertheless, I believe they are the first ones who had that idea. Later on, it was very popular with a paper from ETH Zurich. And mostly because that has a cool name for that, they called it Deep C. So instead of MPC, and people like that very much. Fortunately, it did not stick. So nobody calls it Deep C anymore. It's data-based MPC, and or actually data. You can also leave the M somehow away if you want. But Deep C is not a good model. So lots of results in that respect, but none of them really looking at the closed loop. What property does the closed loop have? And that's the topic of today's talk. And like in the standard MPC way, right, as I told you, if you don't change your problem, it will not be a stabilizing solution. So you are exciting your system with that MPC controller, and it may drive a stable system unstable. And this is exactly the same here. So we are solving the same problem just in a different way. So it's not stabilizing. And that is really true. So this is experimental data with a 4-tank system that we used for education. It's also a result that is very old, but now used again for the data MPC case. And if you use as a time constant for your prediction horizon twice the time constant of the system, so should be enough, it's destabilizing. So only if you go for 3 or 4 times the time horizon, then you're stabilizing. Anything shorter will destabilizing that boringly simple control problem. So it is an issue in MPC. So what to do, how to get stability guarantees. And the obvious idea to do is use the same thinking as we have from the model-based case. So adding those blue terms that I showed you before, and the simple most way how to do that is terminal equality constraints. So that you are demanding that the end of your horizon, you are at the origin where you want to be at your set point. So you are only allowing trajectories that satisfy that. Of course, for those people not in the MPC field, this doesn't mean you are going there over your horizon, because you're just implementing the first piece and then you're shifting your horizon. And then, of course, the carrot that is in front of the stick is moving forward. So you are only asymptotically approaching the steady state. But nevertheless, this is a way how to prove things. It's called zero state terminal constraints, and we can do the same here. Now, what is a zero state here? We have to do the same trick as before. we have no state. We only have inputs and outputs. So what we do is we demand that we have input-output pairs that stay at the steady state for at least as many time steps as we believe our system has maximal in order. So this is the equivalent of the zero terminal state constraints. And if you make the normal assumptions that you have, so nothing, I don't want to talk about it in detail, leave it there for a second for the MPC people that they can check. But nothing strange going on here. So very normal assumptions that you have to take, and then you can prove the normal things that you prove in MPC. Namely, if you have a feasible solution to your optimization problem at any point in time, you know for sure that in the future you stay feasible. It's called recursive feasibility. It's the key in any MPC design. And then the second thing, what you deduce usually from that is the online stability. Here we get exponential stability of the closed loop. And you also have to prove that you satisfy your constraints for all times, which you can also do. So we have, if we add that simple term, that red term, we have all the nice properties for an MPC. And this can be, well, the proof is slightly different from before, but it's of course not a good solution, because if you force solution trajectories to be at the steady state after as many steps as you have prediction horizon, you're limiting yourself. It's not really possible. So you have to do something else, and you can do exactly the same as in the model-based case, quasi-infinite horizon MPC ideas, so that you have a terminal penalty term, a terminal constraint. And now the interesting thing that I'm not going to talk about here is that you can compute those based on data. So you don't need a model to compute those, but you use data, but not Willems fundamental lemma, but a different approach you have to use in order to compute it. But it's possible to compute those. It's possible to extend it to economic MPC, but let me talk about something that's more important. Namely, at the moment, we were assuming we can measure our output precisely, and that is not the case, of course. What we always have is measurement errors. And those measurement errors usually kill this description that we have so far. And we have even two sets of errors, right? We have this one trajectory pair with which we fill our Willems fundamental lemma Hankel matrices. And of course, the output there is disturbed. So it has a measurement term that I call epsilon here. So there is a noise on top of that. And also in our online data that we are measuring, we have a noise term. So 2 times you have noise entering your system. For simplicity, I am only assuming here that the noise is bounded. So, and that the bound is the same for the 2 things. That's only for simplicity of exposition. You can do anything there. And in fact, talking about Roberto, that would be where he would jump in and would say, yeah, sure, there is lots of things to be done. And this is really possible. You can have a distribution there. You can have them differently. And it leads to slightly different results. The simple most to present is this one here. Now, what can we do? We have this description here, this Hankel description. And if you have noise in your YD measurement trajectory and noise in your output measurement, in the Y bar, then this equality doesn't hold anymore. And then the way how to do it is you just relax it, right? So you're adding some sigma here because it's not true anymore. But if you add the sigma here, then it will be true for some sigma. But what you do not want is an arbitrarily large sigma. Of course, we can fulfill that equation for any sigma. So you want a small sigma. So we are just adding a term to our regularization term to our objective functional, demanding that the sigma gets not too large. And for numerical reasons, you are also regularizing with the alpha. If you are interested in that, I can talk about that more. So in the noisy case, which is the robust case, which is really a robustness that this gives us, we add 2 terms here to our objective functional. Here we have noise here, we have noise there, we have the sigma here, and we let the optimizer pick the sigma. So that's the nice thing about MPC. Anything that you don't know, hey, the optimizer should pick it. Of course, you have to prove later on that this leads to something meaningful, but this is how it works. So now we have a more realistic thing. And in fact, this is like an output disturbance that we are having here, the sigma, right? So what we are doing here is really robustifying the method. And for that method, you can prove again that things holds. Again, under standard assumptions, we can prove that we have recursive feasibility, that we have constraint satisfaction, and that we have some sort of stability. But now the stability will not be exponential anymore because we have the noise. You can only go to a neighborhood of our steady state. So we have a practical exponential stability. That's a pretty strong result, isn't it? So we don't know our system. We have no assumption on the model. We have constraints. We want to solve an optimization problem. And still, we can prove that these things are true. So actually, I would say it's even a little bit surprising that you can do that. You can extend that to output constraints. You have to do a proper constraint tightening, lots of things. But now comes the really interesting thing. The really interesting thing is how to apply that to nonlinear systems. Now, Willems' fundamental lemma, inherently linear, right? And I do not know of an extension to nonlinear systems. Actually, there are a few things in that direction. We have also done some things in that direction, but nothing, I would say, fundamental that would allow to apply a whole new nonlinear control theory on that basis. But in MPC, we can use a different kind of thinking. And there are two ideas that I want to convey. So let's look at a trajectory. That's our trajectory in closed loop with the MPC controller. We want to go to our set point. And by the way, it doesn't have to be a point. It can be a trajectory or anything. So it's very generally formulated. We start out at an initial condition and we let the MPC controller run for some time. So we get a trajectory, and this is our current measurement, the YT. So we are collecting data on the way, right? This is how the system behaves. And now, while populating this Hankel matrices with offline generated data, let's just use the data that we have here. So where we currently are, where our nonlinear system is, so a trajectory in the corner over there, the car is doing something, and we use that data in order to populate our Hankel matrix. So that is the first idea that we are having. So no offline generated UD-YD, but just using the past data over a window that we have. So we have a moving window of the past, which we also do in a moving horizon observer or something like that, right? And we forget the old terms. And if we have a new measurement, we throw out the oldest one and put in the new ones. No computation needed. You just plug it into your Hankel matrix. A couple of terms have to be changed. And now the setup is exactly the same that we are having. So we have now only that we have a time varying from time to time Hankel matrix here, but everything else stays the same. Now, this doesn't work by itself. So this is not a solution that gives you a proper result. At least we were not able to prove anything. But you need a second idea. And the second idea is the following. Maybe I'm clicking one step further. So what we are doing thinking-wise is the following. So we have this original point, and we have our trajectory that goes to our set point. I'm changing notation here, apologize. So far it was a YS, now it's a YR. It's the same thing. So R equals S in that case. And so we are using our Hankel matrices to the data to update the Hankel matrices. And now what do we want to do? If we are able to stay in the neighborhood of an equilibrium manifold of our system. So not on the equilibrium manifold, but if we are in the neighborhood of that equilibrium manifold, then we can potentially, and we are able to do that, use robustness arguments. We are not too far away from the equilibrium. We have an error that we are getting. We have to capture the error that we are having, and then we can prove that our nonlinear system is doing something. So how can we stay in the neighborhood of such an equilibrium manifold? And now we are doing a trick that also in MPC is done very often. So of course, we cannot compute that equilibrium manifold. We don't have a model, right? We cannot even, you give me a U and a Y, and we cannot even know whether that is an equilibrium. We need a lot of those, and if they stay constant for quite some time, then it's an equilibrium. Only then we know. We have no clue of computing that. But what we can do is we can introduce an artificial point, an artificial intermediate point, not the YR equal YS at the very end, but an artificial equilibrium point that we call U hat S and Y hat S. No assumptions made on that point, other than this is an equilibrium point. How do we get an equilibrium point? Only if we demand that our trajectories stay at that point for at least L steps. So this term here guarantees us that this is an equilibrium point, and it's our terminal constraint that is stabilizing. So it serves two purposes at the same time. And now we are posing as a formulation that we want to get to that point on our equilibrium manifold. We minimize our objective functional, but we should also have a term that triggers that on that equilibrium manifold, we are going to the set point, and therefore we are taking the difference between that intermediate point and our set point and put it also in our objective functional. So essentially, you are asking that the trajectories go down to your equilibrium manifold in between, and that point on the equilibrium manifold comes closer and closer to the YR. Of course, you are never going there. Same thing with the carrot and the donkey, right? So you're only saying, hey, go there. You are still following that trajectory up here, but it keeps you in the neighborhood of your equilibrium manifold. So, and of course, that's all claiming this works. You have to prove it, and you can prove it. That's the interesting thing. So making a number of assumptions that you have to always make, then you can prove that this set point that is really far out of reach. Now we have another advantage, right? That can be anywhere, that set point. So it doesn't have to be, we don't have to be able to reach it in this little steps of over our horizon. So that set point is practically exponentially stable. We have recursive feasibility. We have a guarantee of the constraint satisfaction. And we have all the things that you would assume hold true for your solution. If the noise gets bigger, your practical neighborhood gets bigger, and so on. You can prove that. And then the nice thing is that solution that you have online is just QP. We now added up quite a number of terms here in our objective functional, but they are all quadratic. They all don't harm, right? So they don't make our problem much more complicated. Otherwise, we just have a standard QP that we have to solve, where we update our Hankel matrices, and we get a solution for which we can prove that it satisfies the relevant properties. The proof is absolutely ugly. So the reviewers, maybe in the audience, I don't know, but if you are, thank you very much. They demanded that this paper is split into two parts, and that you can, and nevertheless, it's a 10-page proof. And 10-page proof, everybody proving things knows, then you really didn't understand what's going on. And that is really, I think, really true. It's really a technical step where step by step we are working on satisfying those conditions in a fairly conservative way. And in the end, you can prove that it works. And it really works in practice. This I'm going to show you in the last couple of slides before I'm discussing I'm discussing now, obviously, what we are doing. So before I told you we want to use data, and people are learning models, for example. They do a lot of experiments, learn how to drive with your racing car around the circle. So you do a lot of things, then you learn a model. So we also do some learning if you want here. And the learning we are doing is we are adjusting our model along the trajectory where we are working. But we are only learning locally. So we are not learning what's over in that corner if I have to operate here. And that is something that fits to MPC, right? So there we also, the strength is that we solve the problem locally. So why should I do the learning globally then? That doesn't fit together. You do a local optimization and you do a local learning of your system. Of course, learning is a big word for that. Actually, you're adapting your model, you have a time varying model. If you want to use also big words, it's an LPV solution that you are having. But we can interpret it as a learning thing, and that's a learning that fits nicely to the MPC. Local solutions for the optimal control problem, I only need to have a model that is valid locally and not globally, and this is what this does. And this is not only my opinion, this is a slide that I got from Mario Steyer, And there at the Northeastern University in Boston, Jan LeCun, the Meta Facebook chief AI scientist, also very renowned scientist, Turing Award winner. So he gave a presentation, and this is the recommendations that he gave in the end. And I'm reading to you: abandon reinforcement learning in favor of model predictive control. I'm not using Facebook, but since this moment, I'm thinking about using Facebook. So this guy knows what he's talking about. So what do we have? Our framework that we are having is we have a locally adapting optimal control where our MPC and the learning are both done locally. And what we have is computational tractability. We only have to solve a QP, and we have guarantees. At least we can check things, right? So you have to check a number of things which you have to do online, but you can check them, and if they are satisfied, you know that in closed loop everything works. And now this also works in practice. Is it now 45 minutes? It's okay, yeah. So I very briefly go over some applications. And the applications is a chemical plant, our 4-tank system that went unstable. And I want to show you with the same horizon that it goes unstable, that it's stabilizing, and a more realistic example in the end. And I go through that very quickly. So this is only a simulation, so of a classical continuous stir tank reactor. And I just want to show you one thing. Namely, here are, for one initial condition where you have a set point up here, 3 trajectories, 3 closed loop trajectories. So the red one here is if you assume you have the model, the nonlinear model of your system, and you do a model-based MPC controller with a stabilization term. Then you get the red curve. The blue one here is our data-based MPC controller. The black one, disregard. So that is not really interesting here. And what I want to point out is, of course, the data-based MPC is worse. So if you don't know anything about your system, how can you possibly expect that you get a thrilling performance of your closed loop? No, it will always, or it's not a theorem. It can also be, you can be lucky, and it's better. Normally you get a worse behavior than from the model-based case. And that's to be expected. And that also means you should, if you know something, model it, do it, model it. And then only those terms that you cannot model, you take data-based on top of that. And that's possible. You can use that methodology in a hybrid way. So don't expect anything fancy from that. Second thing is, for the 4-tank system, that was destabilizing with the horizon I showed you before. And here again, you see the whole trajectory of the data-based MPC. And now you might be wondering what is going on here at the very beginning of that trajectory. And now if you have this data-based MPC and you have no offline trajectory that you're using, you need to collect in the very beginning as many data points as your Hankel matrix needs in order to be able to start. So there you have a drawback. For some time you cannot do anything unless you are just using an offline trajectory or something else in order. But here you will not have that. Again, same thing in the very end. So this is going fluctuating around the set point down here, and there is a reason for that. So that is not necessary. You can go there directly with this boring 4-tank system, and you stay at the right height. You just have to adjust your valves appropriately, and that's really no miracle. But if you are updating your trajectory and you're going to your set point, then what happens? Our Hankel matrices are filled with, if the set point would be 0, with zeros. We have a 0, 0, 0, 0 in, 0 out. We agreed before, hey, that's not a good thing. So this methodology gives you a problem the moment you reach your goal. So you have to do something. And of course, there are many ways what you can do. You can stop your updates. You can say, I'm not continuing further with my updates if I'm close to my steady state. You can switch to an offline trajectory that you generated. Here we said, hey, we added yet another term to the optimization problem and said, hey, we are not happy with being constant at the very end. We want a fluctuation. So always give us a delta U no matter what. And then this is the outcome, which I think is pretty good. And this way you can achieve that for the whole time, you satisfy your conditions, namely this persistency of excitation. Many things that you can do that. All of them are practical problems. Now, this is a real application and a really interesting application. And now I'm really running late, so I'm coming to an end. So this is joint work with a colleague of mine, Oliver Zawodny, and they have from Festo a very nice robot. This is an elephant trunk-like robot. It's a pneumatic robot, so it has a lot of pneumatic actuators all over the place, and modeling that system is a nightmare. Or actually, Oliver says modeling that system is a very interesting research problem, and so he already had 2 PhD students working on the model for that. It's damn complicated. You can get a PhD with that easily, but it's damn complicated to do a model. And then, of course, doing a model-based controller design. So our idea was, hey, in principle, we know how a robot arm works. So we have a standard model, but we don't know how the pneumatic works. Let's just, for the pneumatics, use our method. So we just, for that part of the problem, we use data, online data as we get them, and see what happens. And it's not exactly what we have been doing, so I'm cheating here a little bit, but in principle it's what we are doing, and this is the results. So this is over time from one of the segments. There are 27 segments in that robot. And one segment, and we wanted to have a behavior that is just follow a sinusoid, the dashed line, dashed black line here. And this is the controller that they had before, and that controller is not even able to follow that dashed line. You cannot tune it in a good way, and back there also. So the gray shaded areas is the control out of a model-based attempt since many years. Now, what we did is then switch on joint work with them. So it's not work against them, but with them together, we implemented the database part. And then you can see once we switch on the database part, then our trajectory gets better and better and better. And even if we make a set point change, we are following that. If you switch it on, off again, it reverts back to the bad behavior. So it works. And the price to pay, this is an afternoon from my perspective. From the implementation perspective, it was much more. But from the theory perspective, it's an afternoon how to do that, because you don't need anything, right? You just say, this is my optimization problem. This is the terms I want. Here are the data in my system. And it works. And it really works for many things. So summarizing, what we have is an output feedback MPC scheme for unknown nonlinear systems that are disturbed by noise. So pretty big thing. And there are 2 elements to it. One is our different modeling, database modeling, and the second one is a simple local learning. And together we can give for that guarantees. Now, if we come back, as I said, to that slide at the very beginning, what are the things we want to achieve for a good control method? Well, we have it, right? Okay, limits still available, but a quadratic program we can solve for high order. So we can really assume, hey, the order is 100 and it's no problem. We can assume the order is 1,000 and it's still computationally usually not a problem. And we have all those properties now, and we really satisfy all of them. So I couldn't resist in doing that here. That's the MPC Superman, and really it solves the problem. So, but of course, there are many open problems to be still solved there, and many real applications to be done. A couple of even companies are interested in that and are trying that out. The work has not been done by myself. I'm only a co-author on the papers. The main author is Julian Berberich. Most of that stuff is his PhD thesis. There are other people who contributed significantly.